Good morning again, everyone. As I see people still joining the class, I'll kind of break down what we're going to do today. So, I had some technical difficulties with getting Chapter 4, the pre recorded lecture, done and uploaded to YouTube. So, that got done in the wee hours of Monday, I guess, morning. So, clearly, I wasn't expecting for you to be able to look at that before class. If you did, kudos to you. But I also know that you have an exam this week. So chapter 4 may be the furthest thing from your mind, and that's okay. Chapter 4 is going to be broken up over 2 weeks because it is a monstrous chapter. It's quite large. So what we're going to do today is a little bit of exam review. I've got 10 questions that are very similar to the ones that you may see on your exam. The exams are always multiple choice, so I want you to have the opportunity to practice multiple choice questions. So we're going to do questions about 2 or 3 at a time, a total of 10 questions to give you. I focused on chapters 2 and 3. Chapter 1, we talked about what is a chemical? What is chemistry? I figured y'all probably got that on lock. There will be a few questions from chapter 1, so don't completely forget it. But I focus mainly on sig figs, conversions, and some of the stuff about chapter 3 with states of matter, physical changes, chemical changes, that kind of thing. So we're going to start with the exam review. Then we'll get through what we can for chapter 4. And then we'll finish up chapter 4 next week. You do have a chapter 4 check-in, but your mastering chemistry homework for chapter 4 and the quiz for chapter 4 are not due this week. We're not finishing the chapter this week, so it's not due this week. I have reminders as usual, but I wanted to just kind of put it out there in the beginning so that those of you who joined class on time, you can breathe a little bit easier to know that you only have the one assignment. It's a chapter check-in. Shouldn't take you more than about 30 minutes. And depending on what we get through in this class, I may have to modify it a little bit. So, with that said, does anyone have any logistical questions about taking the exam? Respondus questions, computer questions, anything logistical?
I have a question.
Go ahead.
What does the test close?
So the test will be available Wednesday at 8 a.m. and the test will close at 11:59 p.m. on Friday. Now, what I also require of you, in addition to doing the exam, is to upload your work for the math questions. So the work that you show me for your chapter check-ins, that's the kind of work that I want to see for your exam as well. So your exam 1 is going to be in a folder in the course content section. It'll be labeled exam 1, and you'll see the exam. You'll see some instructions. You will also see a periodic table and an equation sheet, which you can print those out. You'll also see an assignment that's called work for exam 1. It's not worth any points, but you must upload your work in addition to completing the exam. So once you finish the exam in Respondus, you have to upload your work as a PDF, just like you do for the chapter check-ins. And if you don't do that, then you lose points. So I can't necessarily give you partial credit, but I can at least look and make sure, and I can give you feedback, because these questions, you may see them again on the final exam. Did I answer that question? I know I gave some extra information about, in addition to when it will be. Okay. Next question.
Okay, so responders will allow you to have two periodic tables, so that will allow you to have that open.
So there are 2 options, and what I've seen work better is if I give you the periodic table as a PDF and then you can print it out. Or if you have a periodic table that you've used from a previous class, you can use that. I can also put it as a link so that you can open it with the first question and just keep it open. Anything that you open through the exam, you can keep open. So if I posted something, a link or a website or something like that, as long as it's through the exam, you can open it and it'll stay open as long as you don't close it. But what I've seen work the best is if you just print out the periodic table and the equation sheet. You're welcome. Other logistical questions? If you think of them as we go along, that's fine. Are we ready to start the exam review? Okay, then let's go. So what we're going to do is I will give you a few minutes to work on the questions on this page, and then we'll go over them. So right here I have 4 questions. I'm going to give you, let's start with just the first 2. I'll give you 5 minutes to work on the questions, and then I'll go over them. And it's not just about going over the concepts. I'm also going to try to give you some multiple choice test taking skills, because you won't have all day to do this exam. So you need to be able to kind of get through the multiple choice questions. And if you can reason your way through and rule out some answers before you even do any work, that's the best scenario. So take 5 minutes. It's about to be 11:09. So I'll check back in at 11:14 and see how we're doing. Go for it. Let's go ahead and get started. What do we get for the first question? You have to choose the one that has the correct number of significant figures designated to it. A, B, C, D, or E. I agree with that. But just for fun, let's go through and figure out how many sig figs the rest of these guys actually have. Well, maybe it's not fun, but it's good practice. So for A, how many significant figures are there really in this measurement? Yeah, there should be 3 sig figs there. We said B is already correct. What about C? How many sig figs? I agree. Y'all been studying. I see it. Number 4. Letter D. All right. So let's remember, when we're talking about a decimal, you have to get to some non-zero digits first. And those are the ones that start counting as significant figures. So for D, we have 4 sig figs. The first 2 zeros are placeholders. And what about E? How many sig figs do we have? Yep, we've got 3. All right, what do we get for the next question? Which one is the correct answer for this calculation? Is there a question?
Yes, sorry. My audio went out when you said B is only 4.
Yes.
Okay, thank you.
You're welcome. So I agree with this answer. It is E. Now, here's a way that you can rule out 3 of these answers without even touching your calculator. The first thing you should do is figure out how many significant figures should be in your answer. You have 2 sig figs in 36, and it's pretty clear that that's the fewest number of sig figs. So if you do the multiplication, that answer has to have 2 sig figs. Then you do the division, that answer as well, 2 sig figs. So you can get rid of 3 of the choices off the bat before you even touch your calculator. Those are the kinds of tips that I'm trying to give you so that you can rule out answers and not second guess yourself. Because if you had to choose between D and E, then you might be like, wait, maybe it is 3. I don't know. This looks more like what's on my calculator. Sometimes your brain is a little bit different when you're taking a test than under normal circumstances. So you have to take that into account and try to set yourself up for success. Yes.
So you said that for these kinds of problems, since both multiplication and division have the same rules, we can just put this whole thing in the calculator and then determine significant figures.
Yeah, you can, and it'll work out just fine. But if you have addition and multiplication or something like that, then your book wants you to separate out those operations and figure out the number of sig figs after each operation.
Okay, thank you.
You're welcome. Other questions?
Yes, I have one.
Go ahead.
Are we going to be like the charts or the measurements of the metric system, the SI system, things of that nature? Or is it you told us to print out?
You will not get those charts. You will get conversions like US to metric conversions, but you will not get the chart that has the prefixes. Alrighty. Let's do these other 2 questions. I'll give you 3 minutes for these because it shouldn't take you that long. So it's about to be 11:19. I will check in at 11:22. Go for it. And what do we get for this one where you have to choose the number of decimal places that's correct for this problem? So we got a mixture of answers. We've got B and we've got C. So let's remember the rule for adding. When you're adding or subtracting, what you want to go with is the fewest decimal places. Here we've got to the thousandths place. So I put TH for that. We've got the hundredths place, the hundredths place. So that means our answer needs to have the hundredths place. The only answer that has that is C. Is everybody clear on that? So adding and subtracting, we're looking at the number of decimal places. And since the fewest decimal places is 2 decimal places, that's what we need to have in our answer.
Can you explain that a little more?
Sure. So
Remember when I'm sorry.
go ahead.
I was gonna say, like, remember when we first started learning about this, and we lined it up vertically using the line of excess numbers that we can match, like the line of decimal points. Wait, so is that like what we would do for this too?
Yes, and I was actually going to do that as the longer explanation. Yep, exactly right. So if you line these up, And remember, don't add any zeros. That's what you're told to do when you're first learning how to add and subtract, that you fill in zeros in places. Here, that's not going to help you. So I draw my line so that I know, okay, right here, whatever digit this is, that's going to be the last retained digit. And the digit that is directly to the right of it is what I'm going to use to round. So on the exam, you can write it out like this and then draw your line so that you don't get confused. Otherwise, if you know, okay, I've got 3 decimal places, 2 and 2, my answer needs to have 2 places after the decimal. If your brain can do that without writing it out, then go for it. Does that help?
Yes, it did. Thank you.
You're welcome. Jordan, did you have a question still? Right. Excellent. What do we get for the next one? Which of the following is the largest unit? This is just straight up memorization. Yep. So you got to know those prefixes. Otherwise, you will not be able to do this question. So how do we feel about those first 4 questions? Good, meh, man, I need to study. Okay. Let's move on. Good. So hopefully this will help clear some things up, brush the cobwebs off. So I only put 2 questions on this next slide because one of them is a conversion question. So you will get this kind of information like I'm circling. You won't need to know, by memorization that 1 kilogram is equal to 2.2 pounds. That would be pretty evil. So whenever there's a conversion like that, you will get that information. So it will be on your equation sheet. Anything that you need that will help you with a conversion or an equation, it will be on the equation sheet. So go ahead and do number 11 and number 12. I will give you... Oh, is there a question? Yes. So I'll go over that again at the end of class. But yeah, I'll talk about the exam and how it's going to be formatted. You'll have to print off your periodic table and an equation sheet. And those things will all be in a folder along with your exam in the course content section. Alrighty. I will give you guys, let's see, another 5 minutes to do these questions. The first one shouldn't take that long. The second one is a conversion question, so that will probably take the bulk of your time. If you don't finish it in 5 minutes, that's okay, but we just don't have unlimited time in the class. So I'll let you go until 11:33, and then I'll check back in. Does anyone need more time to finish this second question? Alrighty, then I'm going to assume that we're ready to go. So for this first question, which of the following conversion factors is a measured number? I agree. Do we need an explanation for that? For those of you who may not have gotten it? Okay. All right. So, Here's the difference between E and all the other ones. All of these others are definitions. When you say 1 dozen, the meaning of a dozen is 12. The meaning of 1 foot is 12 inches. But the meaning of 1 gallon is not 25 miles. So that's one way that you can figure out whether or not a conversion factor is a measured number or if it's a definition. If it's a definition, then it is not measured, it is exact. Does that help clear it up some? Okay. I knew that was going to get some people. So that's why I put it in there. What do we get for this next one where you have to, there's a dose of aspirin of 5 milligrams per kilogram of body weight to reduce fever of an infant? I agree with C. So I'm going to write out the calculation that I did to get there, just for those who may have been lost or they didn't get it right and they don't want to share their answer. And it'll be helpful if you review this video or look at the PDF for the notes. So the first thing you have to do is take those pounds and convert them to kilograms. Then you take the number of kilograms and figure out how many milligrams of aspirin you need. Your calculator will tell you this answer. You need to know that you can only have 2 sig figs. So that's 19 milligrams. And I will label these. So we're going from pounds to kilograms and kilograms to milligrams of aspirin. Yes, what's your question? Yes. Well, in this case, so I'll give you 2 answers. For this question, when you do the math, C is the only one that is even remotely close to what you get on your calculator. Everything else is far off. So if you set up the equation right, then the only answer that makes sense is C. But what we're looking at here is the information that we're given in the problem. We're given 5.0 milligrams, so that's 2 sig figs. 8.5 pounds is also 2 sig figs. And some of these, when you look at the US to metric conversions, whichever one has the 1 in it, that's going to be your exact number. Okay, so the 1 kilogram is exact. What's measured is the 2.2 pounds. And that also has 2 sig figs. Everything has 2 sig figs, so your answer should also have 2 sig figs. Does that help? You're welcome. Go for it. Right. Exact numbers do not make any kind of impact on the number of significant figures you have, because an exact number has an infinite number of significant figures. So we just don't even think about it. Yep, that's fine. That's fine. Other questions, or are we good to move on? Go ahead. Yes. Look for your measured numbers and then figure out how many sig figs they have. Then you do your problem. Yes, in this case, because we're doing all multiplication and division. Great. So how do we feel about these two problems? I know there were several questions for number 12. Well, I say number 12. This is pulled from an actual exam. So these questions are real. All questions, all of the questions that you will see in our exam review are pulled from actual exams.
So like so you wouldn't cross like you don't cancel out any like you see the 1 kg like you wouldn't cross or cancel those out in this problem.
Oh,
Like
I
you wouldn't cancel one, but like if it were like if it were like a number you would multiply or you would like I don't know
I know what you're asking. Yeah, I know what you're asking. Let me see if I get it. So let's say that instead of 1 kilogram is equal to 2.2 pounds, it was 5 kilograms is equal to 2.2 pounds, right? Which we know is not correct. That is not correct. But if it were, then you would have 8.5 times 5 divided by 2.2 times 5 divided by 1. Does that answer your question?
yeah. But like you wouldn't cancel out the kilogram or anything, but it would still like the problem would still stay
Right.
in a okay.
Yep.
Thank you.
You're welcome. So are we good to move on? All right. We've got a few more questions, and then, yes, it would still be, if I put, let me go back. So for this, in this case, since I only put 5, these would both be, this one would have to be measured. One of them has to be measured. But in that case, 5.0 would give you 2 sig figs because 5 kilograms equals 2.2 pounds. It's kind of a weird example to do, but technically, yeah, if we call the kilogram still the exact number, then we wouldn't care about how many sig figs it has. Go for it.
What exactly is 5 kilograms equals 2.2 pounds?
It it doesn't. This was an example to go over. Let's say that it was you had a different number here in the numerator when you were multiplying and dividing through. That was what the question was. So if in some alternate universe 5 kilograms is equal to 2.2 pounds somehow, then you would set up the equation where you'd be multiplying 8.5 times 5 and then dividing by 2.2. You're not canceling out the number, you're just canceling out the units. So that was to clarify that portion, okay? Alrighty. So now we've got a couple of questions about density. So I'm going to give you 5 minutes to work on these. Then I have another couple of questions on chapter 3 stuff that won't be math. So 5 minutes for this. We'll probably take another 3 minutes for the next set of questions. And then we'll have some kind of Q&A a little bit before we start chapter 4. So it is about to be 11:44. So I will give you until 11:49. Good luck. Let's get started with the first question. If you have an answer, you can go ahead and put it in the chat. Absolutely. You don't have to ask. Take care of yourself. Let me know you're okay. Just make sure that you email me and let me know you're okay. So we've got 2 answers so far. Let's let some other folks weigh in. Or if you didn't get an answer, you can let me know that too. That is helpful. It's not just about the answer, it's about how far you got to, so I can help you. So I'm going to start solving the problem, and then we will clear up which answer it is. So there are 2 concepts that you need to understand to be able to do this first question. The first one is knowing what specific gravity is. Specific gravity talks about the relationship of a density to a substance to the density of water. The density of water is 1. So, if we say that our specific gravity is equal to 13.6, then that means the substance, in this case mercury, has a density. Hg is the symbol for mercury. Then that means that its density is 13.6 grams per milliliter. So that's the first part. You have to know how to get the density of mercury from the problem. The second part is understanding what density is. Density is the mass divided by the volume. Yes, what's your question?
You said the first step was getting density from?
The first step is figuring out what your density of mercury is. We're given a specific gravity, not the density of mercury. For the question, we have to have, the density of mercury. So we know that the density is equal to the mass divided by the volume. And you'll have this equation on your equation sheet. We know that we have a mass of 0.35 kilograms. And we're looking for what that volume of mercury is, which is milliliters. So let's first rearrange our equation. If we have the mass and we're looking for the volume, you can either isolate it and kind of solve it using math, or you can write your density as a conversion factor. So I'll show the conversion factor way because that's kind of what your book does. But if you are a math person and you like to just rearrange equations, that's totally fine too. So our density of 13.6 grams for every 1 milliliter and 1 milliliter for every 13.6 grams. Hopefully you see the problem that we have. The mass we're given is in kilograms. Our density is in grams per milliliter. So before we can actually solve anything, the first part of our equation needs to be taking these kilograms and converting to grams. Now we'll have grams, and then we can choose our conversion factor. We want to end up with a volume at the end. So we should put that at the top and grams at the bottom. When you cancel your units, you should get milliliters. Your calculator is going to tell you something like this. There's some more numbers after that. And what you need to know is, well, I've been given a specific gravity, which was 13.6. My density is 13.6, and that has 3 sig figs. But the mass that I've been given only has 2 sig figs. So I can only have 2 sig figs. So that means 26 milliliters. So if you got D, it's because you didn't convert kilograms to grams. Go for it. So no, it's just how the math works out. So with specific gravity, we're looking at the density, we're comparing the density of the substance to the density of water. The density of water is 1. So if your specific gravity is larger than 1, then your specific gravity also tells you what your density of the substance is. But if it's less than 1, let's say that our specific gravity was equal to 0.7, then you'd have to do the math to figure that out. And it would end up being less than 1. Yeah, you're welcome. Other questions about this one? So if you understood the method, but you didn't convert the kilograms to grams, then you would end up getting D. So watch your units. Are we good on this one? Let's do the next one. What did we get? We've got a mass of 2.00 liters of intravenous glucose solution, and we have a density of 1.15 grams per mil. I agree with that one. I'm going to show how to do it. So there's 2 ways to do it, or 2 ways to think about it, okay? The first way I'm going to show you is the way that will never steer you wrong, and it's what you were taught to do in terms of conversions. We have 2 liters of solution, but our density is in grams per milliliter. So we have to first say, well, how many milliliters are in 1 liter? So that will convert from liters to milliliters. Then you can take your density and write it as a conversion factor. So we've gone from liters to milliliters. And now we've taken those milliliters and converted them to grams using a density conversion factor. That's what we've done so far. But notice that we have kilograms for our answer. If we stopped here and then tried to find an answer, it would be wrong. So we now have to figure out how many kilograms we have. And this is where knowing those prefixes is going to help you. So if you don't know them, commit them to memory. When you do all that math, you get 2.3 from your calculator. Now, if this was a free response answer where you had to report your answer using the correct number of sig figs, if you just wrote 2.3, you wouldn't have the correct number of sig figs. We've got 3 sig figs in our volume and 3 sig figs in our density. So in order to have 3 sig figs, we have to add a 0. So I'm writing the added 0 in red. So how did that one feel? I know a few of you put in your answer and you got it right, but there are more than just 3 people in this session. Okay. Whoa, I think there are 2 people at the same time. So let's raise our hand first and then, so we don't have that happen. Okay. We can go over it again. Let's see what the question is, and then we'll try to do both at the same time. Okay, we can handle that when we go back over it. So is the general consensus, can we go back through that again for those who didn't get an answer? Okay. So go for it. Mm-hmm. So the other way to do it, which I don't want to confuse anyone, so cover your eyes, cover your ears if it's going to confuse you more. So the relationship between grams and milliliters is the same thing as saying kilograms per liter. So you can use the 1.15 and say 1.15 grams per milliliter is the same as 1.15 kilograms per liter, as long as the relationship between grams and mils is conserved. So that's what you may have done kind of in your head. As long as you can kind of show me that a little bit, I understand in a test situation, it's kind of like, okay, I'm putting together all the things I know, which isn't just from the textbook, but just from life. So just show me something that you didn't just, and if you guessed, that's fine too. Just say, I guessed on this one. But give me a little something to show me how you got to your answer. So whatever work you did would probably be okay. So this over here is its own little separate beast. If that doesn't make sense to you, don't worry about it. You can do dimensional analysis and it will make sense. So we have a mass of 2 liters of solution, and we're given a density in grams per milliliter. Liters and milliliters are not the same. So we have to convert something. And it's easier to convert your volume of 2 liters to milliliters first. So when you do that, you're going to have your first conversion factor to go from liters to milliliters. So that means that you've got 2,000 milliliters of solution. Same thing as 2 liters. Then you're going to use your density as a conversion factor to figure out the mass of your 2 liters of solution. So that's where this comes from. You can write your density as a conversion factor by writing it out as a fraction. And then you choose the one that's going to give you grams. So that means you want the one with grams at the top. This last step, we had to do this because all of the answers were in kilograms. So if we stopped here and multiplied 2,000 times 1.15, we would get an answer that you didn't see. It being grams. Everything here is in kilograms. So you have to convert your grams to kilograms using the 1 kilogram over 1,000 grams. Does that help? Walking through it again. Are we ready to move on? Okay. So here's the last few questions. And these are chapter 3 questions. So I will give you 5 minutes to do these. We'll go over them. And then if you have any other questions about the exam, we can talk about that too. So 5 minutes. That means I will see you back at 12:15. All right, y'all. This is our last set of questions. What did we get for the first one? An ice cream sundae is it's a heterogeneous mixture. So it's absolutely a mixture. But there's the ice cream, there's whipped cream, maybe some kind of chocolate. Okay. Next one. Which one of the following properties describes a liquid? So we had a few people say C, but the answer is D. So think about it. If I gave you a cup of milk, literally 1 cup of milk, 8 ounces of milk, and it fit into, a little measuring cup, and then I told you to pour it into a 16-ounce container, will that fill the whole container? No. It's only going to fill it about halfway. So it does not fill the entire volume of the container. So these other ones has a definite shape. That's a solid. Particles move very rapidly. That's a gas. Fills the entire volume of the container is also a gas. We established that D describes a liquid. And there's essentially no interaction between the particles. That is also a gas, because the particles are so far apart that they pretty much don't see each other. So make sure that when you're reading through these questions that you have an example in your mind. Because if you thought about that cup and you had a set volume and you pour it into a different cup, then you wouldn't have chosen letter C. So I'm telling you, use an example in your head and go through it for solids, liquids, and gases, and that will help you. Sometimes these multiple choice questions are tricky. All right, the next one. Which of the following would not be a physical change? I agree. What is D? Burning gasoline in a lawnmower. What is it an example of? It's a chemical change. Good. And this last question. Which of the following is a chemical change? I agree. Hopefully you're not burning the sugar, though. That would be bad. But caramelizing sugar, that's bomb. All these other ones, we're talking about physical changings. So bending a steel rod, that's a physical change. It's a change of shape. Making a snowman, cutting a rope, melting gold. None of those things have to do with changing the chemistry or the composition of any compounds. They're just kind of changing the shape or changing the state of something. So how do we feel about those questions? Yeah, it's okay. All right. So that concludes the exam review. We covered chapter 2. Well, we did cover a little bit of chapter 1. We talked about sig figs. But don't forget that there's interpreting graphs. Yes, we're going to take a break after this. So if I just wanted to give the opportunity for any questions about the exam before we go to a break. Go for it.
So I know like the homework and like supposed to be there was more conversions and math in chapter 3. So on the test, is it only going to be like math and stuff from chapter 2, or you just wanted us to review this part of chapter 2?
This is not a comprehensive review. So there will be more math. We did do like the heat conversions and things like that. But since we just did that last week, I wanted to take the opportunity to review chapter 2 math to make sure that you can still do that. So you still need to know all of the stuff from chapter 3, like we did specific heat. We did those heat calculations. So those are still fair game as well. This was more of a review the previous chapters and also give you an idea of the types of questions that you'll see.
Okay, thank you.
You're welcome. If there are no other questions, we can take a 10-minute-ish break. Okay, I see another hand. Go for it.
So for some of the problems like the density problem, it was like an equation so like density equals mass over volume. If we like converted it from liters to milliliters, can they use that formula? Would that be okay? Or would we have to do some conversion factors?
It would be okay as long as I can see how you got from point A to point B.
Thank you.
You're welcome. Okay, now we can take a break. I want to make sure that we can get through some of the chapter 4 stuff. I will warn you that whatever we don't get through today for chapter 4, we may or may not be able to get through it on next week. So I wanted to take the time to do the exam review. Other instructors may not be doing exam review. So it's a kind of a pros and cons approach. But hopefully the review was helpful. So let's break until 12:30. That's 7 minutes. And then we'll get started with chapter 4. See you in 7 minutes. All right, everyone. It's 12:31, so that's my bad. But we're going to get started with chapter 4 now. The first part of chapter 4 isn't really groundbreaking. If you've had any chemistry before, you've probably seen this. But I want to go over it just to make sure that we're all on the same page. Now, I know that I posted the chapter 4 pre-recorded lecture late, had some technical issues. Please still watch that. There's going to be some more detail in there that we're not able to get to. So make sure that you watch that as well before you do your chapter check-in. So the first thing we're going to go over is the elements and their symbols. So elements, you should remember from chapter 3, are pure substances. And all of matter is built on elements. So all the things. You cannot break elements down any further. There's nothing simpler than an element. You break it down beyond the point of being an element, and we're not talking about matter anymore. If you have a textbook, you will have a periodic table on the front cover, like inside the front cover. On the periodic table, there are chemical symbols, and they represent the names of the elements. They have either 1 or 2 letters, and it always starts with a capital letter. So here are some examples of 1-letter symbols like carbon and nitrogen. And then there are 2-letter symbols like calcium and aluminum. Nothing groundbreaking here. So I'm going a little bit fast just to make sure we get through it. But if there is something that you don't understand, let me know. Because I've still got my eye on the chat. You can always raise your hand and ask a question. Now, I'm not going to take a lot of time to go through all of these common names and things like that, but I do want to give you a few landmarks for how to interpret your periodic table. The first is you're going to see vertical columns and horizontal rows. The columns are groups. The rows are periods. The way that I remember that is I write group and period just like you see. So the groups are the columns, the periods are the rows. Groups are elements that have similar properties. So they have similar physical and chemical properties. Periods, we're just talking about going from left to right on the periodic table. There's no real similarity there. You do have an increase in atomic mass and an increase in atomic number, which we're going to define atomic number, as you go across a period. And finally, there are some common group names. So group 1 or 1A, which, let me cover that first too. So we have representative elements, which if they're using the older system to label the different groups, have an A behind them. The transition elements are the B elements. So they have a number and then the letter B after them. Some of the representative elements, the groups, have names. 1A is the alkali metals. Now I go into detail in this with the video that's on YouTube. So there's specific slides for each one of these. But here I'm just going to kind of give you the crash course so that you can be introduced to the material. And then when you have the opportunity to go and watch the lecture, which is about an hour, it won't be foreign and you may be able to get through it a little bit faster. But again, if you have a question, feel free to stop me. We're going to do some practice problems too. It's not just going to be me talking at you until 1:30 because that would be terribly boring. I would fall asleep. So I don't want to do that to you. So we have the alkali metals for group 1. And they are very reactive. So if you put sodium or lithium or any of the things in this first column in water, they will react quite violently. You can see videos of it on YouTube. If you are bored or you like chemistry, look it up. Then there's the alkaline earth metals. They are still quite reactive, but not as reactive as the group 1A alkali metals. You can see alkaline earth metals in fireworks like strontium. We don't really talk about the transition elements. They're there. And there's no common names for a lot of these groups on the right-hand side. But you will need to know group 7A is the halogens, and they are quite reactive. They can form compounds with pretty much every element on the periodic table. So they are quite reactive. And finally, 8A, those are your noble gases. The noble gases, they don't do chemistry with anyone. They're a pretty elite club. So you will need to know the names of these and the groups. You'll also need to be able to maneuver around the periodic table. So if I told you to tell me what the element is in group 1, period 5, you would say, okay, this is group 1, and then count 1, 2, 3, 4, 5. And whatever this element is, you would be able to tell me that. So from here on out, you're going to need a periodic table. You're going to need it for your homework, and you're going to need it for exams and things like that. So I've posted a periodic table in the Chapter 4 folder under course content. That's the one that you'll get for every exam, and it's the one that you can use for your homework if you don't have a book. Are you with me so far? Just gave you kind of a lot of information, but it's really more of a what you need, the type of information you need to know. Yes. Yeah, just the ones that have names. So group 1, I use the A term. So 1A, 2A, 7A, and 8A. Those are the common group names that you need to know. Okay, great. So I'm not going to go through this learning check, but when you have a periodic table in front of you, I want you to try this. I will put the answers up. I will put the answers in after our class is over so that you can go back and check your work if you check the annotated notes. But this is kind of what I was talking about, where you have to find the element that is described. So group 7A, you have to be able to find that on the periodic table. And then period 4. So it's the 17th column, or the one that's labeled 7A. And then you count down 4 rows. So that's what you need to be able to do with the periodic table. Again, we're not going to go through these now, but when I post the notes for this live lesson, the answers will be circled. We clear on that? Okay. The next big piece that I want to talk about is the characteristics of metals, nonmetals, and metalloids. Most of the periodic table is made of metals. Large majority. And I have in the recorded video a periodic table that shows you visually the metals, nonmetals, and metalloids on the periodic table. The characteristics of metals, well, they're shiny and they're ductile, which is just another word for malleable. And they conduct heat and electricity pretty well. Most metals are solids. Mercury is an exception, but generally speaking, metals exist as solids under our normal atmosphere and temperature and all that stuff. And when you think about the characteristics of a metal, you can kind of relate to it because you encounter metal every day. We don't really use money that much anymore. Everybody's sliding their cards and using Google Pay and Apple Pay and all that stuff. But you maybe have seen a penny on the ground or something, right? And you can think about the qualities, the physical qualities of a coin. It's shiny. We all know that. And the conducting heat and electricity well, think about the pots and pans that you use to cook. Those are made of metal, so they conduct heat really well. And they don't melt at lower temperatures. You can put a cookie sheet in the oven at 400 or 500 degrees Fahrenheit. It's hot, but it's not even beginning to melt. The electricity piece, you may not think about it, but if your computer is plugged in or you're charging your phone, the lights are on in the room that you're in, you're using electricity. The wires that bring electricity to your home from the power plant or the sub plant, those have copper or aluminum in them. So metals can be extruded into wires and they can conduct electricity. So these are all examples of metals that you know in everyday life. I recommend that you just know the characteristics of the metals, because then when you have to compare to non-metals, you can just think it's the opposite. Metals are shiny, non-metals are dull. Metals are ductile, meaning they're malleable. You can pound them, you can extrude them into wires and all these things. Non-metals are brittle. If you use pencils, sometimes when you're writing, you break off the pencil point real easy, or you see the graphite dust on your paper. You can grind it into powder. You can't really mold it into anything. And they're really poor conductors. They have lower densities and lower melting points. So it's literally the opposite of everything metal. So are we clear on the differences between metals and non-metals? Now, I don't have anything up here for metalloids, but pretty much it's a mixture. So you can't really generalize for a metalloid whether it's going to be shiny or dull or ductile or brittle. They have their own characteristics, but the one thing you can say is that the properties of metalloids consist of a mixture of properties you see in metals and properties you see in nonmetals. And that's as much as you really need to know. They're also good as semiconductors. They're better conductors than nonmetals, but again, there's nothing that we can really say specifically about metalloids other than their characteristics are a mixture of metals and nonmetals. I talk about the location of the metalloids and the nonmetals in the Chapter 4 lecture on YouTube. So again, make sure that you watch that in addition to what we're doing right now. The next big topic I want to cover is the atom. We'll talk about a little bit of the history of how we got to understanding the structure of an atom. And then we'll talk about the actual structure of the atom. So in the 1800s, there's a man named John Dalton, and he did a lot of observing nature. And then from those observations, writing theories and laws and things like that. And one of the things that Dalton did was he wrote the atomic theory. This is where he describes atoms. Just based off of observing compounds and elements, he came up with these 5 points that describe atoms. First, he said that atoms are tiny. We know that. And it seems kind of like no duh to us because it's 2020. But in, I think it was 1803 or something like that, when he was writing the atomic theory, it wasn't exactly something that you could just assume. Even the idea of an atom was revolutionary. So it really doesn't matter where you are in time in terms of how these ideas are perceived. Anyway, atoms are tiny. Atoms of an element are similar to each other. So if you have 5 aluminum atoms, they're going to be similar. But if you have 5 aluminum atoms and 5 iron atoms, those 2 groups are going to be different from each other. You can combine atoms of different elements to form compounds. Remember that compounds are also pure substances. So that's a reach back to chapter 3. Just a reminder, all of this stuff builds. So you need to remember your terminology even as we go forward. Finally, he said, atoms can be rearranged to form new combinations using chemical reactions. And that during those reactions, you never create or destroy atoms. So these are all things that kind of make sense. We already know this just from life, from having previous chemistry classes, but you will need to know these 5 points for Dalton's atomic theory. So do these points make sense? They're kind of common sense, like when you talk about chemistry, but I want to make sure that they're clear. Yes. Okay, it sounds like you answered your question. No problem. So some time passes. I'm sure people are still thinking about the atom and trying to figure out what makes up an atom. But it's not until around the 1900s that J.J. Thomson starts doing work with cathode rays. And in doing his work, he discovers these negatively charged particles, which we now call electrons. And he also was the one to figure out the charge to mass ratio for an electron. Then he starts working on a model of the atom, which he calls the plum pudding model. And I'll show you what that looks like on the next slide. But it says that An atom is just kind of like this cloud of positive charge, and there are little dots of electrons like plums in a pudding. So in this case, plums are raisins. Okay. Let's see what that looks like. So if you have your kind of sea of positive charge, that is the pudding. Okay. And then the electrons are the plums, or again, the raisins in the pudding. What this also says is that most of an atom is empty space. Because electrons are really tiny. So it's pretty much a big ball of nothing with some electrons in there. That's his plum pudding model. Now, J.J. Thomson, he had a lab and he had students working with him. And from those students, some of them went on to also do work, and they were great contributors to the field. And one such person is Ernest Rutherford. So Ernest Rutherford had a lab, and he and one of his students, Hans Geiger, came up with this gold foil experiment. They wanted to test the plum pudding model. If the plum pudding model is true, then that means that I can shoot particles at a piece of matter, and those particles will just go straight through because it's mostly nothing, just air, right? Empty space. So they set up a source of alpha particles, which are large and they're positively charged. You set up this source and you send a beam of particles to this thin gold foil, which is why it's called the gold foil experiment. If the plum pudding model is true, then you'll have your gold foil and all of your beams, all of your particles will go straight through and they won't be deflected by anything. But, yes, there's a question. Yeah, they're large, positively charged. You don't need to know that for this. Just know that they're large particles. We'll actually talk about alpha particles when we do some nuclear chemistry, but you don't need to know that for this chapter. Okay. So if the plum pudding model is supported, then that's what they would see. All of the particles would go straight through. However, what they actually saw was that some of the particles were deflected. So they went through, hit something, and then the angle of the particle changed. So that means that there must be something there that's more than just empty space. Let me see if nope, didn't put that in here. So there's another slide that I have in the pre-recorded lecture that goes a little bit more into detail. They saw deflection of some particles. Some of them went all the way through, but some of the particles were deflected or scattered. That means that there must be some kind of dense mass in the atom that can deflect these large particles. And that dense mass was given the term nucleus. So you will need to understand the basic details of this experiment. If it doesn't 100% make sense to you now, it's fine. Again, make sure that you watch the video because I spend a little bit more time going through it, and I have additional slides that will clarify, what the experiment is, what the observations were, and what they mean. But those are the three things that you'll need to know. Kind of the setup, what the results were, and the interpretation. So is everyone clear on what you're going to need to know for the gold foil experiment? Yes. Yes. So Rutherford has his own model of the atom. After he saw, okay, this plum pudding thing, that ain't working out. He was a great mentor. I got on my feet, but his model was wrong. So Rutherford says, here's my model of the atom. You've got a nucleus in the center, and then in the empty space around that nucleus, you have your electrons. And this is the Rutherford model. And this is pretty much what we use today. We know there's a nucleus. We know that the electrons kind of hang out around the nucleus. So there are subatomic particles that create or that make up the atom. Protons and neutrons are located in the nucleus, and that was the dense mass that those particles encountered that caused them to deflect or scatter. There's symbols for all of these particles and their relative charge. So the protons are positive, electrons are negative, and neutrons are neutral. They have zero charge. We have their relative masses. The proton and the neutron are about the same. Electrons are really, really small. And of course, their location in the atom. Protons and neutrons are in the nucleus. Electrons hanging out on the outside. This shouldn't be super incredibly new. If you've had chemistry before, you should know protons and neutrons and electrons. If you don't, that's okay. Just let me know. But I'm kind of working on the assumption that this information, while some of the detail like the Rutherford's gold foil experiment and things like that may be new, the concept of an atom having a nucleus and subatomic particles is not news. So is that a fair assumption to make, that we all kind of already know this table more or less? Okay, good. So let's just do a quick learning check to make sure that we're all on the same page. I will give you a minute to go through and do A, B, and C. So to share our answers, you can put P for protons, N for neutrons, and E for electrons. So what is found outside of the nucleus? Or you can just put them all. All right. So electrons are outside of the nucleus. What has a positive charge? P for positive, right? What has mass but no charge? Neutrons. So if that was not elementary to you, again, it's okay. Let me know. Watch the video, but hopefully this part should be pretty easy. Now we're going to talk about the atomic number, and we're going to talk a little bit more about some of the information that you can get from the periodic table. So down below, there's an example of what you might see on a periodic table. You've got this number on the top, which is the atomic number, and then you have a symbol. In this case, this is the symbol for sodium. You will not have to memorize the element symbols, but you will need to be able to make your way around the periodic table. Now, what is this atomic number? The atomic number is the number of protons. It's always going to be a whole number. You can't have part of a proton. And each element has the same number of protons. So all sodium atoms have 11 protons. If it has 12 protons, it is not a sodium atom anymore. And again, that atomic number always appears above the symbol of the element in a periodic table. Let's add on a little bit more terminology. So we've got our atomic number, and I'll throw in the symbology here too. So protons, P plus or P. The mass number is going to be the number of protons plus the number of neutrons. So it's just what is in the nucleus. That's your mass number. If you want to figure out the number of neutrons that you have, then you're going to take that mass number and subtract your atomic number, which is the number of protons. Now, we really only talk about mass numbers when we're talking about isotopes, and we'll talk about isotopes in just a second, but you're not going to see the mass number on the periodic table. So this is what you might see for carbon. Its symbol here. What is this number up top? What does it mean? Right, it's the atomic number, which is also the number of protons. There's another number here that you'll see underneath the symbol. This is the atomic mass. So don't get those two things confused. The other way that you can see an element represented is using atomic symbols. So if we were to use carbon again, if we were to see carbon again, the atomic number would be down here below as a subscript. And the mass number, which is the total number of protons and neutrons in the nucleus, would be up top as a superscript. The third way you can see this is by writing out the element or the symbol for the element, followed by a dash, and then the mass number. So I go into detail and take it a little bit slower on the video to introduce atomic symbols and what all the pieces of information mean. But you will need to be able to interpret these three different ways of representing an atom and its mass number and its atomic number, particularly for isotopes. So you may not understand all of the concepts, but do you have an idea of what you're going to be responsible for? Okay. Yeah, there's a question.
So atomic mass and mass number separate things.
Yes, they are two separate things. And we're going to talk a little bit more about both of them in just a minute. So if you can hang on, I will continue to clear up the difference. So before we add on the complication of atomic mass, I just want to take a second to do a little practice with you guys on practicing the relationship between atomic number, mass number, the number of protons, and things like that. So I'm kind of going to walk you through this first one, and then on your own, you can do practice to fill in these other two rows. You will need a periodic table to do this. So, the name of the game is fill in the parts that are missing. And you have to identify the element that's represented. The way you can identify an element is by its atomic number. So if you have a periodic table, you can look up the element that has a 9 above its symbol. If you do that, you will see that it is fluorine, and its symbol is an F. We know the atomic number already, so we can put that as our subscript below. But we still don't know our mass number just yet. Let's see what else we can fill in. The atomic number tells us the number of protons, so we can put that in as well. Our mass number is the protons plus the neutrons. We have in our table that there are 10 neutrons in a fluorine atom. So if we add 10 plus 9, that gives us 19 for the mass number. And we can fill that in. This is our atomic symbol. Now we still have this question of electrons. When we're talking about atoms in this way, we're talking about neutral atoms, which means they have no net charge. So the number of protons is equal to the number of electrons. You have to have the same number of positive as you do negative so that your overall charge is 0. So if you have 9 protons in a neutral atom, you have to have 9 electrons to balance out the charge. So just to make sure that we understand that concept, in this second row, there are 15 protons. How many electrons do we have to have in this atom for it to be neutral? We have to have 15. Again, that may not be fluid to you right now. That's okay. I do more of this in the video that's on YouTube, so make sure you watch it. I will fill in the answers for this practice problem as well before I post the PDF. Yes, what's your question? Yeah, there's a whole folder of chapter 4 stuff. It's in course content. No, there should be a link for the chapter 4 lecture too. If it's not there, maybe it's hidden for some reason, but there's absolutely a video. So I will check that out right after class and make sure that it's posted. Yeah, no problem. Yeah, if I'm talking about something and you're like, okay, she says it's there and it's not there. Maybe it's not there. It could be hidden, or it could be some weird setting that I need to change in Blackboard to make it available. So don't feel like you're stepping on any toes if you say, Dr. Hefner, I don't see that. That's totally fine, because maybe it's not there. Okay. Okay. I'll just double check and make sure. But there should be a link for the lecture video, the lecture notes, a video on electron configuration, which we're not covering in this part. That's in the second part of chapter 4, but I just wanted to put it there. And then there's your chapter 4 part 1 check-in and a periodic table. So there should be 5 things in there. Yes, chapter 4 lecture part 1. There is going to be a part 2. I have that ready pretty much already, and that will be what we cover next week. So it's the second half of chapter 4. No problem. So let's try to get through this. There's a few more slides and then we'll be done. So I mentioned isotopes when I was talking about mass number. And remember, the mass number is the number of protons plus the number of neutrons. I also said that atoms of the same element are similar. I didn't say they were exactly the same. They may have different mass numbers. This means they have the same number of protons, but there's a different number of of neutrons. So instead of there being 5 neutrons, maybe there's 7 neutrons. That doesn't change the fact that it is, was that boron? It's just a little bit heavier. So when you're writing your atomic symbol, the mass number gives you more information about that particular isotope. So magnesium, there are, I believe, 3 naturally occurring isotopes. There's magnesium 24, magnesium 25, and magnesium 26. And the only difference is that magnesium 24 has 12 neutrons, 25 has 13 neutrons, and 26 has 14 neutrons. Still the same number of protons. So is that clear about an isotope? Same number of protons, but their neutrons are different. Now this is important because we talked about atomic mass a little bit as this decimal number that's underneath the symbol. The way that's calculated is you have to know all the naturally occurring isotopes of that element. And then you do what's called a weighted average, where you take into account the percent abundance of that isotope and its mass. So another example would be chlorine, which there are 2 naturally occurring isotopes. The more prevalent one is chlorine 35. About 3/4 of all the chlorine on the earth has a mass number of 35. The other 25% of chlorine is a little bit heavier. It's got an extra 2 neutrons. So when you figure out the weighted average, you're taking into account how much of each one there is, in addition to the mass of each of these. So the final thing I'm going to do is walk you through. This is the same example that I do in the video. And this is how to calculate atomic mass using a weighted average. Now, you've encountered weighted average before. Your grade is a weighted average. Master in chemistry is worth this percentage. Participation is this percentage. Exams, final exam. They're not counted equally, but they all add up to 100%, and it gives you your grade. It's the same idea here. Your car might still have a CD player in it, but you probably don't use it because most people either listen to the radio or you're listening to your iPod or something like that because you can hook it up through Bluetooth or all that stuff. So CDs are outdated. But back in my day, like high school, everybody had their big old CD pack with all the stuff. You know, you go to the music store, which music stores don't exist anymore, and you get the latest CDs and stuff because there was no streaming. I'm a dinosaur. It's okay. I'm fine with that. So, gallium is found in the lasers used in CD players. And there are 2 isotopes, gallium-69 and gallium-71. We have our percent abundance here, and we have the mass of each of these isotopes. And the question is asking, what is the atomic mass? Whenever you see that question, you should automatically think that you have to calculate a weighted average. I like to organize the information in a table so that I've got all my ducks in a row and I can just do the calculation. Because sometimes you won't have every bit of information that you need. You may have to solve for a piece of information before you can calculate your mass. Obviously, we have to write down each isotope. So we've got gallium-69 and gallium-71. We're given a percent abundance, which is how much of the gallium in the world is gallium-69 and how much is gallium-71. I'm going to make another column here, but I'm going to leave it blank because we're going to fill that one in last. Right now, we're just filling in the information that we have from the problem. So atomic mass, I didn't go over this specifically in this lecture, but in the video I do. It's measured in atomic mass units or Daltons. So when you're giving an answer for this type of a problem, make sure that you have a number followed by AMU. So those are your units. These are the bits of information that we got from the problem. We have all the information we need to solve, but I like to make it a little bit easier. I like to express my percent abundance as a fraction. You can also do it as a decimal, but your book does fraction. Either way, you're going to get the same answer. So with percentages, if I say 60.10%, that means 60.10 over 100. That's how you can write that as a fraction. So how would you write 39.90% as a fraction? Exactly. 39.90 over 100. Now we've got everything that we need. And what you're going to do is multiply this fraction by the atomic mass it's associated with. You're going to take that product and add it to the product of the second abundance expressed as a fraction times its atomic mass. And that will give you the contribution of both of the isotopes. So I will write it out in one long string so you can see exactly what that looks like. So this is what you're doing. The number that you get for this first part of the calculation will tell you the atomic mass contribution from the gallium-69 isotope. The second part is the contribution from the gallium-71 isotope. For the purposes of doing mastering chemistry and all of that, you're going to want to calculate each of these numbers individually and take into account sig figs. Then you add them together and take into account sig figs. Give that a shot in your calculator and tell me what you get. You can just give me the calculator answer, that's fine too. In the interest of time, I'm going to start writing down what you should get when you do each step individually. So your final answer should be 69.72 AMU. When you do each individual part, these are the numbers that you should get when you take into account significant figures. So it's as easy as that. If you make the table, it will make your life a lot more stress-free. So it may not 100% make sense how to put this together, but how do you feel in terms of if you were to watch another problem, you think you'd be able to do it? We don't have time to do another problem, but do you feel like, okay, I think I kind of get that? Good. if there are questions, I'm going to ask that you hold them for 1 second so I can get through my reminders and remind people about the exam. So you have a Chapter 4 Part 1 check-in that is due on Sunday the 20th. That's on Blackboard. It's already there. Due Sunday. It's 4 questions, 20 points. The Mastering Chemistry Chapter 4 homework and quiz is not due until September 27th. We have not finished covering the chapter yet, so I can't have you do the homework. But I do recommend that you try to do the homework associated with the sections that we've covered this week. It will make your life easier. Then next week, you can do the remaining sections and the quiz. So don't leave it all for next week unless you absolutely have to. Try to do some of it this week, ask your questions about it, and then finish it up next week. Finally, Exam 1. We did exam review at the beginning for a reason. It covers chapters 1 through 3. So everything that we've covered in these live lectures and in the recorded videos, all of that is fair game. The review that we did does not cover every single concept that we've covered in class. The exam will be available at 8 a.m. tomorrow. And it will disappear Friday, September 18th at 11:59. So you need to start it and you need to finish and upload your work by 11:59. So you've got 3 days to do it. You must use the Respondus Lockdown browser and monitor. The issues with that have been fixed. If you do encounter an error, please take a screenshot of it and send it to me via course messages. I've been a little bit lax on answering emails instead of saying, hey, you need to use course messages, but the university is being a little bit more firm about that. So I have to be more firm. If you send me a message via email, I will respond to you saying, hey, I'd love to answer your question, but it's got to be through course messages. So send it to me there, and then I'll be happy to help you. I'm not trying to be a jerk, but I am trying to do what I am told. Yes, there's a question.
I've been trying to like send emails through course messages, but it only gives us like students in the class even sometimes I can read emails.
So you should see my name listed. So you have to scroll down and find me. So yeah, do that for course messages in Blackboard. And it helps me out because then I don't have to ask you, which class are you in? Which section are you in? Because I don't have that in my brain. More about the exam. Very quickly. To find it, you're going to go to course content, just like you do for all our other stuff. There's going to be a folder called Exam 1. There's going to be some text underneath that folder that's going to give you instructions on how to take the exam. It'll tell you you need to print out your periodic table and your equation sheet. Don't skip through the exam because once you hit that next button, you can't go back. So there is no skipping around. You answer that question, lock in your answer, and then move on. You get one question at a time. So make sure that you've got enough time to do your exam. I'm going to allot you 1.5 hours. It should be plenty to do your exam. This does mean that if you have an internet issue, you'll get kicked out of the exam and you will not be able to restart it. So if that happens, I need to see some documentation about that. I need to see that you got kicked out. So if you can you can show me that it's no longer available, and I will be able to see that you have an attempt started. Okay? So if you have some kind of internet connectivity issue, then you'll have a problem. Otherwise, once that timer goes off, you're done. So 1.5 hours to complete the exam. Multiple choice. Make sure you print out your equation sheet and your periodic table. Are there any questions about that? If you don't have questions, you're free to go. It's 1:32. Otherwise, hang around and ask.